Welcome to your exam masterclass. Let's jump straight in. Today, we're decoding the essential shortcuts, the unbreakable rules, and those incredibly sneaky examiner traps for mastering atomic forces and polarity. Honestly, if you've ever felt like chemistry grading is just a series of tricks meant to trip you up, you are in exactly the right place for this explainer. We're going to break down exactly what the examiners want to see and give you the tools to ace it. Here's our study checklist for today. We'll be hitting the electronegativity rulebook, running through periodic trends and shortcuts, predicting bond types, mapping out molecular shape and polarity, and capping it off by mastering intermolecular forces. Okay, let's kick things off with Section 1, the Electronegativity Rulebook. We're starting with the absolute golden rule of this entire module. Right off the bat, I need you to commit this exact phrasing to memory. Electronegativity is the power of a particular atom that is covalently bonded to another atom to attract the bonding pair of electrons towards itself. Examiners love asking for this specific one-mark definition. And pay attention to the keywords here: covalently bonded and attract the bonding pair. Don't fall into the trap of just saying it attracts electrons in general. It specifically has to be a bonding pair in a covalent bond. Lock that detail into your memory bank. If you take exactly one thing away from our time together today, let it be this. Fluorine, sitting proudly up in the top right corner of the periodic table, is the ultimate electron bully. We use something called the Pauling scale to assign an electronegativity value to each atom, and right there at the top is fluorine with a perfect 4.0. It is literally the best element at dragging electron density towards itself when covalently bonded. Everything else, well, they're just playing catch-up. Moving right along to Section 2, periodic trends and shortcuts. Now that we know who the reigning king is, let's look at some shortcuts so you can predict element behavior without memorizing the whole table. When that exam paper asks you exactly why an atom's pull changes, please don't just guess. These three factors are your bulletproof answer. First up, nuclear charge, which is just the number of positive protons in the nucleus pulling on those negative electrons. Second, atomic radius, the literal physical distance from the nucleus to those outer bonding electrons. And third is shielding, the number of filled inner electron shells wedged between the nucleus and that bonding pair. Think of atomic shielding kind of like trying to see a concert stage while standing behind several rows of very, very tall people. The nucleus is the stage, the bonding electrons are you trying to watch the show, and the inner electron shells are the tall people totally blocking your view. The more shells an atom has, the more they mask or shield that positive nuclear charge. And the result? A much weaker pull on those outer bonding electrons. So how does this actually play out? Well, as you move down a group, you're stacking on more of those shielding shells, the atomic radius gets way bigger, and so electronegativity drops. But as you move across a period from left to right, you're packing more positive protons into the nucleus without adding any new shielding shells. That pulls the radius in tighter and spikes the electronegativity. Your absolute best exam shortcut here? Just look at your elements and ask yourself, which one is closer to fluorine? Because the closer it is to that top right corner, the stronger its pull. All right, Section 3, predicting your bond types. With our trends locked in, we can use a little simple math to predict the exact kind of bond that'll form between any two atoms. You're going to want to write this ultimate cheat code down right now. By finding the numerical difference between two atoms on the Pauling scale, you instantly reveal the relationship status of their electrons. If the difference is below 1.0, they're sharing those electrons pretty fairly. That's a standard covalent bond. If the difference lands between 1.0 and 2.0, things are getting unfair. That's a polar covalent bond. And if that gap is massive, like greater than 2.0, the more electronegative atom just straight up steals the electron, creating an ionic bond. So here's what that unfair sharing actually looks like on your exam paper. Let's say you've got hydrogen bonded to our bully fluorine. Hydrogen is a 2.1, fluorine is a 4.0. That gives us a difference of 1.9, dropping it squarely into polar covalent territory. Whenever you sketch out a polar bond on a test, always draw a dipole arrow pointing straight toward the bully atom. And definitely don't forget those little delta positive and delta negative signs. They are absolutely crucial for tracking the partial charges, so the examiner knows you understand exactly where the electron density is pooling. Which brings us beautifully to Section 4, molecular shape and polarity. We're scaling up from a single flat bond to a whole 3D molecule. And let me warn you, this is where so many students fall straight into a classic examiner trap. Listen closely to this one because I see this trip people up all the time. Remember that not all molecules with polar bonds are polar molecules. Seriously, Just because you have a polar bond tucked away inside a molecule does not automatically mean the entire molecule itself is polar. The whole game changes when you consider the 3D arrangement. The shape of the molecule dictates absolutely everything. Let's see how this trap actually springs. Imagine a molecular tug-of-war happening in 3D space. For a molecule like trichloromethane, you have 3 highly electronegative chlorine atoms all yanking the electrons down toward one side of the structure. Because they're all pulling in a similar direction, the whole molecule becomes lopsided. It's asymmetrical and polar. But now look at tetrachloromethane, 4 chlorines perfectly spaced out in a tetrahedron. They are pulling exactly equally in 4 completely opposite directions. It's a dead tie. The poles cancel each other out perfectly. So even though it's packed with 4 very polar bonds, the overall molecule is totally nonpolar. Shape really is everything. And finally, Section 5, Mastering Intermolecular Forces. Let's take everything we just learned and apply it to the weak, invisible forces that exist between completely separate molecules. These are the forces that actually dictate physical properties, like boiling points. Believe it or not, even perfectly nonpolar molecules manage to attract each other, and this 4-step sequence is your bulletproof, full marks exam answer for how it happens. We call these instantaneous dipole-induced dipole forces or London dispersion forces. Step 1. Electron clouds are constantly moving, and just by sheer random chance, they slosh over to one side. Step 2. Boom, a split-second temporary dipole is born. Step 3, that temporary negative end repels the electrons in a neighboring molecule, which actually induces a temporary dipole over there. And step 4, those newly formed delta positive and delta negative ends attract, forming a weak force. Memorize that sequence. To really see why these fleeting temporary forces matter, just think about the noble gases. As we move from helium all the way down to xenon, the number of electrons in the atoms goes way up. And the more electrons a molecule has, the larger its charge clouds are. Larger charge clouds mean it can form much larger temporary dipoles. Bigger dipoles means stronger attractive forces between the atoms. As a result, it takes a whole lot more energy, meaning a much higher boiling point, to actually rip them apart and boil the liquid. Now let's compare those temporary forces to permanent ones. Think about propanone versus butane. They both have roughly the same number of total electrons, right? So their temporary, induced forces should be about the same. But check out their boiling points. Butane boils right around 0 degrees Celsius, while propanone needs a whopping 56 degrees to boil. Why? Well, propanone contains an oxygen atom which creates a highly polar carbon-oxygen bond. It has a permanent delta positive and delta negative end. Because of this, it acts like a sticky magnet to its neighbors, forming permanent dipole forces. These strong permanent connections easily beat out the weak temporary forces of butane, giving it that much higher boiling point. Well, we have covered a ton of ground today, from those fundamental electronegativity cheat codes all the way to the 3D tug-of-war rules. So before you go, I want to leave you with a classic exam challenge. Look at these 3 molecules: chlorine, hydrogen fluoride, and the V-shaped sulfur dichloride. Take what you've learned today, grab some scrap paper, sketch out those shapes, draw in your dipole arrows, and test yourself. Are they polar or nonpolar? By applying these visual shortcuts, I promise you'll be racking up those exam marks in no time. But honestly, beyond just passing a test, ask yourself this. If these invisible split-second tugs of war are dictating whether something boils, freezes, or shatters, what other hidden forces are silently shaping the physical world around you right this very second? Thanks for hanging out with me on this explainer. Keep practicing those sketches, and good luck.